Study Unit 2, Lecture 2. This lecture will focus on different resistor types as well as several properties of resistors, specifically the thermal properties of resistors. So an important aspect to consider when designing a resistor or designing a system which uses power resistors is the continuous power rating of the resistor. The continuous power rating of the resistor is determined by the maximum surface air temperature of the environment where the resistor is, the stability of the resistance when it is subjected to a DC cyclic load. In other words, what is the stability of the resistance as a current through it turns on and off. And lastly, the continuous power rating is determined by the proximity of the resistor to other heat sources in the system or the environment, as well as the airflow in the environment. High airflow obviously means that more heat can be dissipated. So in any environment, the temperature rise is determined by conduction, convection, and radiation. Conduction is the movement of heat from one object to another. Convection is the transfer of heat through the environment through air currents or some other fluid. And radiation would be something like thermal radiation, which radiates in the infrared spectrum from a heat source. In general, changes in temperature lead to changes in resistance. In other words, if the temperature changes, the resistance of the resistor will also change. The hottest part of the hottest part of a resistor is the hotspot temperature, and the hotspot temperature is given by this equation over here. TH is the hotspot temperature, or the hottest point on the resistor, and it is typically in the center of the resisting element. This hotspot temperature is given by the ambient air temperature, the thermal resistance between the hotspot temperature and the air, and the average power dissipated in the resistor. The maximum hotspot temperature is limited by the ambient air temperature as well as the average power dissipation and the thermal resistance between the hotspot and the power dissipation. If the air temperature starts to increase, this decreases the average power which can be dissipated in order to not approach a hotspot temperature, which would result in a failure in the device. Once the hotspot temperature approaches the air temperature, the power dissipation, or the allowable power dissipation, will decrease to a point which approaches zero. In other words, no power can be dissipated in the resistor as the ambient air temperature approaches the maximum hotspot temperature. Conversely, if the air temperature is low enough, then with some resistors it is actually possible to dissipate more power than the resistor is rated for because the temperature is so low. Shown here is a cross-section of a resistor which has been clad in an aluminium heatsink. The thermal resistance is determined by the ability of heat to move from the heater element, in this case the resistor, and transfer that heat into the atmosphere. By adding a heatsink, the surface area through which heat can be dissipated is increased, and this will increase the operating temperature that the resistor can operate at. It's important to note that if a resistor is being used which has an aluminium heatsink or any other type of heatsink, and the heatsink area is reduced, then this will effectively reduce the maximum power that can be dissipated in the resistor, and this needs to be taken into consideration when designing. In other words, any decrease in surface area below the rated surface area will decrease the maximum power that can be dissipated in the resistor. This reduction in rated power rating is called derating. Shown in figure 25.9 here from the text is a series of graphs which show the power rating of resistors where the chassis area which is covered by the heatsink has been reduced. Shown here are 5 different resistors: 10 watt, 25, 50 watt, 100 watt, and 150 watt resistor. And it can be seen that as the chassis area which is covered by the heatsink is reduced, the maximum allowable power dissipation of each resistor will also decrease. For the 10 watt example here, the decrease is not that much, but for the 150 watt resistor, just a 50% reduction area has already reduced the maximum power that can be dissipated by 30% from 150 to 100. Resistors intended for use in a high power application will have an overload rating. The overload rating will effectively specify how much additional power above the normal operating rating of the resistor can handle. So this overload rating can either be specified in a short overload for a period of a few minutes, or in how many overloaded pulses can be passed through the resistor in repeated bursts. In other words, what is the resistor's capability to handle a higher load over a short period of time, or what is the resistor's capability to handle a very high load over a very short period of time. For very short pulses, so typically less than 100 milliseconds, the thermal capacity of the resistor will absorb the energy without dissipating heat to the environment. What this means is, as the energy is passing through the resistor will have a certain capacity to absorb heat before it starts to re-radiate or dissipate that heat into the environment, and this is the thermal capacity of the device. If the pulse rate through the resistor is very high, then the repetitive pulse behavior will be slightly different than for overload ratings. At very high pulse rates, so in the order of several kilohertz or several thousand times per second, the peak power may exceed the maximum rating, but because the pulse is so short, the average power which is dissipated in the resistor will be within the maximum power rating of the device. For example, for a metal film resistor, if the pulse duration is between 1 microsecond and 100 milliseconds, then the dissipated power is the square root of 15 divided by the pulse period. These types of relations are generally derived empirically, in other words, from measurements, in order to determine what the average dissipated power rating will be for a particular resistor structure. Shown here in 25.11 from the text is the maximum permissible power dissipation. This is the actual pulse duration. So there will be some limit, which is the single pulse limit. In other words, that is the most power that can be dissipated in a single pulse. If, however, the pulse is within this limit, then depending on the length of the pulse, the amount of average power which can be dissipated will vary. So this graph shown here is for a particular 2.5 watt metal film resistor, and it can be seen that the shorter the pulse duration, so down here at the bottom of the scale, the maximum permissible peak pulse power will be higher, and as the pulses get longer, the maximum permissible peak pulse power will actually decrease. So if the pulses are in the order of microseconds, then the allowable peak pulse power is a few hundred watts. But as the pulses approach the millisecond length, the maximum allowable or permissible maximum average power starts to approach less than 10 watts. Resistors can also have a stability and endurance rating, which is a description of how stable the resistance of the resistor will be under certain operating conditions. So in the example given here, the spec sheet might state that for 1000 hours at some power dissipation Pmax, the hotspot temperature will be limited to 375 degrees, and under these conditions the resistance R will vary by less than 5% of the total resistance of the device. These figures are derived from testing the device at the specified conditions. However, these things are useful to know, because if the resistor is used under conditions which are less strenuous, then the stability and the endurance of the resistor will be better than that of the resistor which was tested under these conditions. Resistors can do more than just resist the flow of energy or the flow of current through the device. Special function resistors also exist, such as fusing, circuit breaking, temperature sensing, and current sensing resistors. Fusible or fusing resistors are resistors which will fuse once a certain power dissipation has been exceeded. What this means is, once a certain power dissipation has been exceeded, then the resistance of the resistor will increase by parts of the resistor literally fusing apart. This means that the rated power dissipation of the resistor will actually increase, but the resistance will also have increased. Circuit breaking resistors are, as the name implies, resistors where the circuit will break open once a certain power level has been exceeded. What happens with these types of resistors is that there will be a metal joint which will melt open and will have to be closed manually using solder. A fusing resistor will still conduct current once it is fused, but a circuit breaking resistor will present an open circuit once the solder joint, or rather the metal layer, has melted away. Temperature sensing resistors can be used to indirectly determine what the temperature is in the environment where the resistor is. How this works is that the resistance of the temperature sensing resistor is a function of the temperature coefficient across the resistor. This allows a change in resistance will cause a change in either current or voltage, and this can be used to determine what the change in temperature is. Current sensing resistors use a special construction to create a resistor that has a very low inductance. This means that these resistors, which typically have a resistance of a few milliohm to 10 ohms, will be placed in series with a current stream, and the voltage differential across this very stable resistor can then be used to determine what the current is through the resistor. A thermistor is a type of resistor where the resistance varies predictably with temperature. This predictable behavior means that thermistors can be used as inrush limiters, temperature sensors, and resetting current limiters, as well as a wide variety of other uses. In a thermistor, the resistance of the device is a strong function of only the body temperature. In other words, the body temperature of the device determines the resistance of the device. Thermistors come in two different types, NTC and PTC. NTC thermistors have a negative temperature coefficient, and PTCs have a positive temperature coefficient. In a negative temperature coefficient device, the resistance will decrease with temperature. In a PTC device, the resistance will increase with temperature. For transition metals or resistors made from transition metals, the relationship between the resistance and temperature is fairly linear and is determined by K, which is a constant which relates the change in resistance to a change in temperature. It should be noted that just because the resistance varies in a predictable manner with temperature does not mean that all thermistors behave as metal alloy resistors, in that the relationship might not necessarily be a linear one, just predictable. NTC thermistors do not strictly follow this linear relationship and have a more complex nonlinear characteristic behavior. For this reason, depending on how the NTC thermistor is biased, it can operate in different modes. In resistance versus temperature mode, it is quite self-explanatory. Depending on the temperature, the resistance through the NTC thermistor will change. In this way, the NTC thermistor can be used to measure temperature for control which requires temperature as an input. In current over time mode, the thermistor is used in a way that it is biased at a certain point, and then when current starts to flow through the thermistor, it starts to self-heat, and this will increase the temperature of the resistor, and that's the resistance. This can be used to create a delay for current and voltage control in power circuits. In voltage versus current mode, the thermistor will be biased at some point, and then a change in the environment will cause a change in the current through the thermistor and thus the voltage. So in these ways, the thermistor can be used as a sensor. And this concludes this lecture.